Okay, so this video comes after a big overview of chapters 1 through 5, and I want you to understand that because you can watch this video independent of that video, but it does help if you have the time to watch that one. It was about 40 minutes long. So, all right, this is now the discussion from where that left off of how we've branched from the beginning of just collecting data and having the terms of experiments defined to um, to summarizing data, to uh, specifying things like measures of centering, measures of variation, to describing probability and using probability to create probability distributions, which we started in chapter 5, specifically with the binomial probability distribution, to where we are now. So let me actually draw that out, and I will start a new page here to do so. And get that picture down for you. So let me see here. Basically, here's what you need to know is that there's data out there, and there's different ways, and there's different types of data out there, different ways to consider it, and different actual types. Um, and so we took data and we started to do things like create frequency distributions with them. And so those were the tables where we would have, some sort of, some sort of class, and then some sort of frequency. And, we'd fill out that class from here to here, and then there'd be the corresponding frequency. And then through the efforts of chapter 4, in fact, I will summarize this by just going right back to that page. Through the efforts of chapter 4, using probability, we merged this into what we had in chapter 5, probability distributions. So let's imagine we have something like that. So as opposed to a frequency distribution that comes from observed data, this is going to be a probability distribution that comes from expected data, expected value, right? Now, in these tables or distributions, because we can look at them in table form or we can look at them in a graphic, these break up into categories too. These break up into the discrete type, pardon the handwriting, and the continuous type. Now in chapter 5 we talked about the discrete type, and one of the types that we talked about was binomial. That one had those requirements that there was a fixed number of trials, they were independent trial events, that the probability of success remained constant, and that they were two category, right? So there were two outcomes. You could think of them as success and fail. And success could have been someone dying, right? I mean, if you were trying to determine the probability of airplane deaths over the Sierra Nevadas, and you thought of them as, and you're taking airplane crashes and how many actually resulted in deaths, which I'm assuming most of them would if you crash over there. But anyway, you could think of them as success being how many marked deaths did we have, and then failure being if they ended up not dying from the crash. So it was just a way to categorize, right? Two category. We had others. Poisson. Let me see if I'm spelling that right here. Yeah, that's it. Two S's. P-I-O. That's an O. Sorry, that's an I. And you can look that one up, check it out, and learn more about it if you want. That wasn't required for homework. All right, now in chapter 6, we're going into the continuous type. And so back in chapter 5, our distributions would look like this if you were to put the distribution in a graphic like this. You could say that there was 0 successes and some probability of having 0 boys or whatever, 1 success and the corresponding probability of having 1, and so on. And then in chapter 6, our distributions are going to look like this. And the difference is because the obvious difference is this one, they're just single strings or bars, and this one they're not. It's all this area underneath here. Now this one, these values would still add up to be 1 or 100%, but it wasn't visualized as area because it wasn't continuous. Here's the difference, is when it's continuous, it's not just that one little height and that little height and that height and that height. It's all of that, all of it infinitesimally close together, right? Looking like area, looking like a shaded in region. And that's why ours now we're dealing with regions and shaded in zones. And so we have whatever the mean is, and we're going to move by standard deviations. And then that's our chapter 6 material. Okay. Now this curve that forms that is called a density curve. Okay, and that density curve occurs by a definition. So it's a function, and we could have called this p of x, but what we're getting here is based on that set's population mean and its population standard deviation, and that's the standard deviation down there as well, we could formulate this curve, right? In fact, I've actually made a dynamic sketch of to help you visualize the density curve. So here's this density curve right here, applied to the specific numbers that I have in right now, and this is what it would look like. But we like to look at more often the standard normal distribution. So what that means is that we would have the mean be 1 and the mean be 0. Let's get that down. And the standard deviation be 1. Okay, and then now if the standard deviation was something other than 1, okay, my sketch is not changing right now. Let me go try a different one, but this would be able to measure for us the area underneath. And so even though it's not as easy as it was with discrete distributions where we would just say, okay, well this is that high, that's that high, that's that high, or those are those probabilities, we can just add them together in the table. And I think if you saw my other video, you remember that. Here's an example of a discrete probability distribution. You can just say, what's the probability of having 2 or more boys? Well, 2 or more would just be the sum of these numbers right here, right? In other words, the sum of these heights, correct? Well, 2 or more is a little bit more difficult of a question because it's not just in a data set that we're measuring discretely, continuously. It's not as easy as if we were measuring it discretely. So 2 or more would be, requiring us to find I can get this to move. Scoot it way over there. 2 or more wouldn't just mean 2, 3, 4. It would mean 2 or 2.1 or 2.3 or 2.4. Now, it doesn't make sense to talk about 2.4 boys, but what about if you're talking about temperature readings and you're talking about degrees of temperature and you could measure this continuously? Or gallons of milk. You could have 2.4 gallons. Okay, let me see if I can go to this one. Yeah, this one probably will move when I move it, so let's see. If I move, right. Okay, there we go. So as I move the standard deviation, you can see that if the standard deviation gets bigger, then the variation widens, the spread will get bigger, right? Scoot this out a little bit so you can see the whole. Okay, as the standard deviation gets smaller, the spread gets smaller, or the distribution gets thinner looking. And essentially what I'm getting at here is that If it's not a standard normal distribution, it doesn't look at like that one that we have on our standard z-score, on our z-distribution table. In fact, I'll go to the pages. This is, if you didn't see that already, this is that formulas and table sheet. And when you're looking at the z-scores, z stands for standard normal distribution. If it's an x value, then that means it's not necessarily standard. If its mean is not 0 and its standard deviation is not 1, so it's not going to follow this table. But we can always standardize those scores. That's the key here. That's the algebra part. You can always convert those non-standard scores, an x score, like if you watched my last video, the age of a Academy Award best winning an actress award for the best actress award. You can take that age 21, you can subtract from the mean 35.7, and you can divide by that standard deviation of 11.1, and that will give you the z-score. And on that example, it was negative 1.32. So it would end up on the left side of 0. Okay, and the standard scores that end up on the right side of 0, meaning that we're taking all the area underneath the distribution from here, would be something like 1.32 and 2.4 and stuff like that, positives. Now inside the table here we've got the area that's being consumed, and if you were to go all the way across, in fact I'll see if I can show this on my dynamic sketch. Let me first of all make this a standard normal distribution where the mean is 0 and standard deviation is 1. And you can see how our density curve turns out nicely, because what we've got in here is our z-score right there. Turned out just to be whatever the x point is, and so f of x is x in and this curve out. We can go from the left to the extreme and the right to the extreme, and look at what it says the area is, 1. Well, that makes sense because the probability distributions that we were talking about even in chapter 5 had to have a total area underneath of 1. So the sum of all the probabilities being 1. And there's a 1-to-1 correlation between these probabilities and the area under this curve, this density curve. And that's going to be true even if it was a uniform density curve, even if it didn't follow this nice functional shape here. All right, so let's see. So the big key for us here is that now we're talking about continuous data. We can have a nice normal distribution and have it be bell-shaped, or there could be a uniform or a skewed, and we're going to talk about how the skewed gets applied to the central limit theorem. The nice part is if it is normal, to find the area under the curve, all we have to do is slice out a rectangle. It could even be a square, but slice out the rectangular piece. All you have to know is the width down there and the corresponding height that it's uniformly distributed by, and multiply that width times that height, and it'll tell you that shaded region right there. So that's easy. Otherwise, you have to use the standard normal distribution, either directly, using the calculations by hand, or indirectly by letting the normal CDF function on your calculator do it, or the normal calculator in StatCrunch or StatDisk do that for you, or NormDist if you're using the Excel spreadsheet. Jumping back and forth and back and forth, here's another example using the area to find the probability. This is supposing that you are taking my class and you know that I regularly finish my class between 50 and 52 minutes uniformly. I never finish earlier and I never finish later. And so if I do, you can calculate the uniform distribution up here, the uniform probability of 0.5, because this distance down here is a length of 2, and we know that the total area under the curve has to be 1. So what would you have to multiply 2 by to make a total area of 1? You'd have to multiply by a half this height of 0.5. Either way, you can reverse calculate what this height is, once you know the total width of the distribution that you're talking about, and then you can calculate what's the probability that I might end class today between 51.5 minutes and 52 minutes. That last half minute there. What's the probability? Well, determine the distance there, which is 0.5, and multiply it by the height. And this little sliver right here is 0.25. In other words, 25% chance that I can do that. Okay, back to the standard normal distribution. This one, again, is only a standard normal distribution if the mean is 0 and standard deviations are 1. So you're going to be counting 1, 2, 3, and -1, -2, -3. Okay, and if it is, then to calculate the area under this density curve, we have to use tools like the distribution table, or like the calculator. In fact, I'll take you to those pages just a sec. So that in the approved pages, you want to go to the old Appendix C page that shows you quickly how to do this. You can go click second vars, and then to get the area that's under the curve, you can put in whatever the lower score is, whatever the upper score is, and then nothing else if it is a standard normal distribution. Just leave these two spots blank, because it will assume by default that the standard deviation is, or that the mean is 0 and that the standard deviation is 1. And I can demonstrate that too. Alright. And I won't go into any more of those details unless you need it, because I'm looking at big picture still. What about if you're not dealing with a standard normal distribution and you're dealing with a non-standard distribution? Well, you can convert that into a standard normal distribution with our z-score calculation from chapter 3. Okay, I know I referred to that already in this video, so it would be like age 21 minus 35.7 divided by 11.1, and that would give you -1.32, so you would have a standard score, z-score right there. Once you know that end point, once you know any of these z-scores, then you can find the left area with the table or those other tools. Now obviously this whole thing can turn around backward, so if you want to calculate, in fact let me draw that in there, but if you wanted to calculate from this, you know the standard score but you don't know the original data score in some non-standard situation where the mean is not 0 necessarily, or the standard deviation is not 1, then you can do this. Turn the calculation around, multiply z by the standard deviation, and add the mean, and then you could find what the data points were. So just use a little bit of algebra to go around. Now on the formula sheet, that direction isn't explicitly stated. The first direction is for both the sample or the population standardized scores. So if you wanted to go that other direction, go this direction, you have to do just a little bit of simple algebra, and you multiply by sigma, you add mu, or you multiply by s and you add x bar. Just keep that in mind. All right, let's do a quick example then of the first direction. So this way. All right, I'll let you read through the problem. You can pause it there, then unpause. Okay, and then essentially what I care about is the mechanics here. So if you have a non-standard distribution, you need to standardize that score. So if we were talking about less than 174, then we've got to find out where 174 is on the standard scale using the standard z distribution. Okay, and that was, again, we talked about that in chapter 3. It's been a while, but just bring it back to your memory. Find that score, and then this will be located on the table. Now if you don't want to do the table, you can actually use the calculator or StatCrunch or any of those other tools, but what you're looking for is left area, and we want to find out what's the corresponding probability in the body of the table. So what we can do is, let's see, I thought they gave it to us there. I apologize. I'll pull the table up off of our formula sheet. That's at least one location you know it will be. And this formula sheet already starts out with left area. You notice that it's area accumulated from the left. Keep that in mind. The advantage to the calculator and the StatCrunch is that they don't restrict you to just left area. You can go either way you choose by putting in the boundaries. So I'm going to look for 0.07. Oh, right there, right? Double check. 0.07, 700ths. Here's 700ths with nothing in the ones place. So that would be the corresponding z-score, and this then would be the corresponding area. In fact, I might as well show you with the calculator really fast. We'll hope to get the same calculation. And here's the appendix sheet that you can use to remind yourself how to do it. So the only thing you don't see is that it says, I'll scoot it over, it says hit second, vars, go down to normal CDF. This is going to C for accumulate, just like the binom CDF we used in chapter 5. Normal CDF, hit enter. Okay, then we need to put in, sorry, a little touchy. Okay, we need to put in the lower value. Now, our lower value, since we're going anything less than 174, or in other words, anything less than 700ths, it's going to be just extremely left. So the way that we create that kind of an effect in the calculator is we just say negative, and we don't use the minus sign, we use the negative symbol down here. We use negative, and then go really small. So I could say negative 10 to the 10th power. That's the way some people like to do it. Or negative 10 to the 10th, 10 to the 100th power, or negative 10 to the 7th power. But that would be an extremely small, extreme number. But I actually prefer just to type in negative 7 nines. 1, 2, 3, 4, 5, 6, 7. Because that should be as good as negative infinity for the calculator. Okay, comma. Okay, comma right here. And then I'm going to put in the upper score. So then the upper score, if I was going extreme, it would be 9999979. If I was going all the way out that way. But I'm just going to go to 0.07. Okay, and then I can leave the mean and the standard deviation untouched because by default it will already assume that those are 0 for the mean and 1 for the standard deviation. Now I said I was going to leave them untouched and see what the result is, so let me go back. And there we have it. We have approximately 53%, 52.79%. Again, I'm taking it visually from the standard number to the percentage form of the number, and there it was again on the table. And it makes sense because if half the data is right here, right, that would be 50%. Then this is just a little bit more than that, apparently about 3% more. Okay, now I could show you StatCrunch, but we're starting just, we're showing all sorts of different ways. While I'm in the calculator, I guess I could show you one more thing about this. So second vars, normal CDF. Remember how we had converted it from their original X scores, from the non-standard scores? You can leave them in the non-standard scores. So I can leave them in. The 172 is the mean, and the 174 is my right bound, and this 29 is the standard deviation. So in fact, I'll do that, and I'll show you this isn't in your background. So I'm going to put in, and if I want to say extremely small this way, I could just say 0. I wouldn't even have to say negative 99999, because extremely small would be 0 over there, since this is already out 172. I'll say negative 2, just for the fun of it. So, but notice that I'm not using a big negative infinity. And then I'm going to go to 174 for my right bound to the shaded region that I'm trying to calculate the area for. And remember, the reason I'm calculating this area is because there's a 1-to-1 correlation or correspondence between area under the normal distribution, or an area under the density curve, and probability of the event. I'm trying to talk and type at the same time. So there's my population mean and my population standard deviation. I hit enter and look at that. I've got 52.74. Why did I get 4 and not 9 like I had previously and that was stated on the table? Well, it's because I didn't go as extreme in the negative, right? So if I wanted to go more extreme, I could get more accurate there. Now this would have been accepted because there's a certain amount of tolerance that the homework allows, and I'm sure that that would have been accepted. If I wanted to, I could go more extreme. I could go negative 100. But notice again that I don't have to go as extreme because I'm not starting from 0. I'm starting from a non-standard mean of 172. Use my right side cutoff value. Okay, I still should probably go more extreme if I want to get that effect. Alright, so you need to understand the non-standard and standard normal distributions. Okay? Because we use them to calculate errors, maximum margin of errors, and other things in the next chapters. Okay. Finally, let's bridge that gap from what we talked about so far to the central limit theorem. In section 6.4, we teach you about sampling distributions of a statistic, proportion or mean or range or whatever. And essentially what it is, and you can read the definition, it's taking subsets of a fixed size, like say this size we want to be, I don't know, n, 5, okay? And we take all possible samples of size 5 and then calculate this statistic that we're looking for, so the mean, for example. So calculate the average of those 5. And then take another sample of size 5, and this is all with simple random sampling, right? So there should be the same likely chance for any sample of size 5 to be picked. So take another sample of size 5 and find its mean. Now, because the sample is different, it's likely that there is a difference in that mean there. Keep doing that, keep doing that, keep doing that. You keep getting a bunch of these means. In fact, here's a good picture of that from another instructor. Imagine that you sampled out, you've got one mean. It comes out over here, you know, let's say 10. Then you get another mean, it comes out over here at like 35. And then another mean that turns out to be 28. And then another mean that turns out to be 7. And then another mean that turns out to be 13. Another mean that turns out to be, I don't know, let's say, if this was 35, let's say 41, 46. Okay, all those means are just numbers themselves, right? So imagine that list of numbers, that distribution of numbers. That is what we mean by a sampling distribution. Okay, now in section 6.4, you did several examples. You did sampling distributions of proportion, of mean, of median, and so on. After you did them all, they tried to get to this punchline, and I just want to show you this slide that kind of illustrates the punchline. So the main idea is that there are some that are unbiased estimators of the population, because remember, those are from samples. There are some that are unbiased estimators of the population parameter that corresponds to that statistic. So for example, imagine that we had, we were selling ice cream at a little store, and we were only in business, unfortunately, for 3 days. And the number of ice creams that we sold were 1 the first day, 2 the second day, and 5 the next day, the third day. But that's the entire population of our business experience because we only lasted three days. Okay, so this is not a sample. This is the actual population, 1, 2, and 3 of sales of ice cream. If you did a sampling distribution of size 2, where you take every possible sampling of size 2, where you take, the first day, and since it's with replacement, you can throw that day's inventory back in there and take it out again. So selling ice cream, 1 ice cream, then selling 1 ice cream. Then you could calculate its mean and its median and its range and all those values, right? Now, incidentally, its mean and its median would be the same because it's a sample of so small, just size 2. Okay? Anyway, you could do that for all the possibilities. How many possibilities would there be, by the way? Well, we learned that in chapter 4. There should end up being, let's see, 3 of them, 2 to the third. There should end up being 8 different possibilities. I mean 9, I'm sorry, because each of these pockets have 3 values that could be filled in there, so that's 3 squared. So here are the 9 possibilities, and again, these are with replacement. So you could look at the first day being picked and then the second day being picked, and that would be a different experience from picking the second day and then the first day. But run all those, list them all out, and then calculate those the means of those. So that's what this is doing here, and now we can compare. So the mean of the sampling distribution of means is 8/3. The mean of the sampling distribution of medians is 8/3. For range, 16/9. Variance, 26/9, and so on, right? Okay, if you were to actually go back to your original data set, and that's why we chose something so small, it's because we can go back and we simply add 1 plus 2 plus 5, which is 8, and divide by 3, because that's how you find the mean. That would be the population parameter. A parameter is that characteristic of the population, right? So it's that quantitative value that describes some characteristic of the population. That would be 8/3, which is exactly what you got when you did the mean of all of these numbers, right? And do that for the other one. Do that for the median. Well, median is a different calculation, right? When there aren't just 2 numbers, it's not the same as average. When there aren't 2 numbers, you have to look at the middle number, which is 2, in the sorted data. Now, if there is 6 numbers in the sorted data, you look at the middle 2, which was positions 3 and 4, and average those. But either way, you'll notice that that would have been 2, which is not the same thing as this number right here. This is roughly 2.7, so bigger, right? Okay, look through the list here, and this table is already illustrating what I wanted to talk about. Some are targeted. Some, the statistic and the parameter match up, and some they don't. Which ones? Well, they're listed right here. The mean is an unbiased estimator. The variance is an unbiased estimator. And the proportion, so here we're talking about proportion, or like the percentage of odd. The proportion was an unbiased estimator. And then the others are biased estimators. They don't target the population parameters that they correlate with. So that is why we talked about sampling distributions. Some target, some don't. The key here is the mean does, and the standard deviation, although it doesn't, can be shown to be off by a constant rate, well, the consistent rate. And that's what the central limit theorem teaches us. What the central limit theorem shows us is that if you take all of those means and you create a distribution of those, so like it's a population of means, it's a sampling distribution of sample means, that center of that population is equal to the population mean. The original, from wherever that data came from, the original population's mean. And the standard deviation, it's not the same, but it's consistently off by square root of n. by a factor of square root of n. So if we just divide the population mean by a square root of n, and n is the sample size that we consistently chose, like on the previous example it was size 2, and you took every possible sampling of size 2, whatever that is, divide, and that's what we'll be off by. Now there are some details that need to be hashed out, specifically that the samples where n is larger than 30, then we just get these results. But the original population doesn't have to be normally distributed. If the sample size is smaller, then the original population does need to be normally distributed. So we better be getting a sample size greater than 30 if we're going to apply this, unless we already know that the population was normally distributed. So you can look at some different examples in the text. I'm not going to worry about that. I want to, since I'm limited on time here, I want to close with this thing. In the multimedia library, there for chapter, I just chose chapter 6. For chapter 6, it's freezing up here. There are several examples. Click on the one that says sampling distribution there, sample distributions. It's down here. Actually, click on any of these. There are great teaching apps on all the different ideas that we're talking about, specifically that central limit theorem, right? But click on the one that talks about sampling distributions, and you will see the sampling distribution occur before you actually get told that this is the case. Here's an example of it. It doesn't look exactly the same as the one that you click on from there, because the one that you click on there, I'll show you here. Or I won't wait for it. It's kind of a copy of this one. This one comes from Rice University. Rice University has an open, I think it's open, but it's an online statistics book. And you can view the one that doesn't require Java. I sometimes have trouble with that. So essentially what your author did is they took stuff from that open book and they did explanations based off of that. So I'm going to do my quick explanation. Take a population, and we're going to grab samples of size 5. So let's say, and that was kind of uneventful. Let me animate it. Let's say we grab 5 numbers there, and we determine their average. Okay, determine the mean, and we drop it down. And we do it again. And again. And again, and so on. Now keep in mind, this is what we already talked about, right? If you keep doing that, if you take a sample of size 2, like we did in the other example, or size 5, then you can get an average of that group, and then that's a number. Do it again and again and again and again, you get a bunch of numbers, right? As a reminder, here's where we did it here. We took a sample size 2, we got a number. Sample size 2, got a number. Sample size 2, got a number. But we're supposed to be taking all possible samples of size 2 from our population, right? And getting all those numbers and creating a distribution out of that, a probability distribution, right? So that's what we did in section 6.4. Keep doing that. I'm going to speed up the process. Instead of taking just 5 where you can see it, I'm just going to go 1,000 at once, then 10,000 times, and another 10,000. And you know, imagine that I've done this forever. And as n is tending to infinity. Maybe one more just for fun. Okay, we have created a new distribution, but how does that distribution compare to our previous one? Well, look specifically at the mean. Okay, the mean of our parent distribution was 16. The mean of this distribution, which is a distribution of means, is not 16. Okay, I pull a little trick on you just because the software is pulling a trick on me. It is 16 because the software wasn't recalculating like it was supposed to. But you'll notice that the standard deviation is different. Here the standard deviation is 5. This is in the parent population. But the standard deviation here is 2.24. Where's that number come from? Well, quick flashback. If we take that standard deviation of the parent population, which was 5, and we divide by the square root of the size of our sampling that we're doing. We're sampling them size of 5 at a time. Then hit divide. We get 2.23, we'll round it to 2.24. We get that. How did I decide, or where did I come up with that crazy calculation? Well, remember that that was the result of the central limit theorem. It says that the mean would be targeted, but the standard deviation, it won't be the same. It will be off by square root of n, a factor of square root of n, so we have to divide by square root of n. Isn't that cool? You can kind of see the central limit theorem simulated here. Now, by the way, you might be a little misled because you also notice that the median turns out to be the same and the median turns out to be the same. What's that saying? That I was wrong on that slide earlier when I said that the median wasn't going to target the population parameter, that the mean of the sampling distribution of medians wasn't going to target it? No, I wasn't wrong. It's just because in this example, it happened to do that. Let's take something that is not so nicely distributed, that the parent population is not normally distributed. Play the same game, but faster. Look what we have here. The mean of the parent population is 8.08. Here, it's 8 7/100. So, and I haven't kept going. I can go on for infinity. You'll notice that it's pretty much the same, right? Or it is the same as you go on. The median, though, is 7 in the parent population and is 8 in this distribution of means. It's not the same. But the standard deviation, 6.22 and 2.79, they should match up by taking 6.22 and dividing by the square root of, we're still using 5, so we're sampling, our n is 5, and it's 2.78, obviously they've got different approximation going on, but that's why we've got 2.79 right there. So that is very key. The reason why this is key is because this distribution here is normal. As n gets larger, this is normal. And that's what we want, even if the original parent population was heavily skewed, so or not regular at all. So let's just draw our own crazy distribution, right? So that's not normal, it's not bimodal, it's not uniform, it's nothing, right? Nothing special. I'm going to do a bunch of them. Look at this. We've got a normal distribution where its mean is being targeted right there, and its standard deviation isn't being targeted, but according to the central limit theorem, we know it's going to turn out by being 9.27 divided by the square root of 5. And we could change this. We could make this be 25. We'd actually prefer it to be 30 because if the parent population isn't normally distributed, we want this to be 30, right? 30 or above. So let's try a uniform distribution this time. Let's try n is 25. Let's run the simulation. Look at that, normal. Skinnier, of course. This skinniness is determined by the, skinny and fatness is determined by the standard deviation. But if I take 9.52 and divide that by 25 square root, which is just 5, I get 1.9, and we're rounding here to 1.9, right? So very, very important result, very important theorem. Very good way to learn the theorem by just going through these animations. Go back here to this page. Going through some of these animations. Okay, I hope that helps. This is a lot of talking, and if it doesn't help, then it's a lot of talking for no good reason. But I wanted you to understand, nothing else we really need to talk about there. I wanted you to understand that those really main the big picture and those difficult points. Hopefully this helps. Good luck, and come back to these pieces and send me a question. I'll try to help.